Okay, hello everybody. It's still morning here on the West Coast, but I know many of you are someplace else. But so we have an interesting set of speakers. I'm wondering, is Katalin Martinas, are you on right now?
Yes, I am here.
Okay, excellent. So Katalin's going to talk to us about thermodynamics for evolution. So without further ado, let's turn it over to her.
That's great. Thank you so much.
Just a minute. I will start immediately.
Can you speak louder?
Could not do it. So,
You need to share your screen.
yes, I do it.
Hello, are you still there?
Yes, it is here.
Okay.
So that is my lecture, Thermodynamics for Evolution. Just a minute. Okay. Do you see it well?
Yeah, it's much better now. Just keep that scale.
That is good. And really, the subject of my lecture will be a new approach to thermodynamics, which I call holistic thermodynamics. And
maybe turn your camera on too.
Once
Turn
more.
your camera is not on.
It is on. Just a minute. Okay, it was on. Yes.
There you go.
Okay. You see me?
Yes.
Oh, wonderful. Holistic thermodynamics is a holistic description of physical system, and really involves to answer for the question what is whether we can answer really in physically correct sense for the biological energy, and the result will be a new quantity that, which I call extropy. But what is holistic thermodynamics? In thermodynamics, when in the there is a phase of thermodynamic theory when what we can call as the foundational part, when we translate the basic laws of nature, which are verbally formulated to the language of mathematics. And in this foundational stage, we have a basic law of thermodynamics. That basic law says that we are obliged in this stage use equilibrium systems. That's why we have an equilibrium thermodynamics, and non-equilibrium systems are described as local equilibrium states. My suggestion is that this basic law is accepted since Clausius. I taught it and I was taught in this manner, but it is only a possibility, but it is not necessary. And so we can start from non-equilibrium systems if we use a holistic description. And in this holistic description simply means that the systems are characterized by global characteristics, so which characterizes the whole. And the most important part that this approach to thermodynamic works, that is the first basic result. Second, in this approach, hidden beauties of thermodynamics will be apparent, And so we will get a very, very, very simple way to introduce the entropy. And and also further parameters which characterize the non-equilibrium systems. But I want to tell you how I did reach this holistic thermodynamics. When I was teaching thermodynamics, I could realize that the energy is a very, very complicated concept. And one cause of this complication can be simply identified in the different disciplines, in the different part of life. The energy has different meaning. It is always connected with the activity, potential for activity, potential for work, but it is absolutely, they are different. And for the evolutionary problem, the most important question, the relation of the energy in biology and the energy in physics. As an example, I will tell you, a simple example, I ask for a glass of water. When I get it, I can ask, what is the energy of this water? And if I am a physicist, and I answer as a physicist, then I can answer with the internal energy of the water. But for the life, for the everyday life, for biology, the answer that the water has no energy. So it is really simple, two different concepts. And my daughter was who summarized very nice way the problem. She was in the secondary school, and I asked her, what did you learn about energy? And she said, energy in classes of physics is a conserved quantity. And on the classes of biology, it comes from the sun and we consume it. So it is clear that they are absolutely different concepts. And my proposal will be that instead of this biological energy, we can use entropy-like quantity, the extropy, and it will be easier and deeper understanding they can show us. So my lecture will consist of 3 parts. The first part is the holistic thermodynamics. The second part, I will show that holistic thermodynamics can be approximated by the irreversible thermodynamics in slow processes. So it means also that the holistic thermodynamics is an generalization of thermodynamics for which incorporates also the quick processes. And in the last part, I will show how these thermodynamics can be applied to biology. I said that holistic thermodynamics is a holistic description of systems. But for system, I use now the definition of systems by systems theory. So system is a separable part of the universe. And be cautious, because this definition does not coincide with the definition that we use in physics. Because in physics, we speak about correlated systems and also systems with long distance interactions. They don't satisfy the separability condition. So for all my discussion, I will consider these systems special systems, and I don't discuss them. So normal systems, which are separable part of the universe, it means immediately that the zeroth law for systems can be applied. And what does it mean, system? I use the beauty of the Hungarian language. In Hungarian language, the word system was replaced by a Hungarian word. Dugonics András did it in the 19th century, and he selected a beautiful word. It consists of two parts. The meaning of the first part is order, and the meaning of the second part is approximately manifold. So the Hungarian word itself shows us the basic property of systems, is double nature, that it consists of several parts, a manifold, but it behaves as a unit. There is an order which is represented by the system concept. And if I take it into account, then I can see that in physics, we have three approaches to the systems. Naturally, we have the traditional, the atomistic one, when all the elements constituting the system are described separately, and the totality of these parameters define our system. That is the atomistic approach. But in statistics, the method to transform these individual parameters to global parameters is already solved. So that is the statistical approach, which describes all global parameters. But the third approach is from the order approach, but the system shows, that is the holistic approach, when we are not interested in all the details, but only essential parameters are selected. And we have a description if the selected essential parameters define the system. And the equilibrium thermodynamic did this task, and it is so it is a holistic description. But from this approach, you can see already that there is no law which would tell us that the holistic description can be applied only for equilibrium system. So we will do it for non-equilibrium ones. And I start now not from the phenomenological description of the systems, but from the global description. So the global variables for non-equilibrium systems are naturally we know the total energy, and the extensive parameters also characterize the non-equilibrium system. So the total volume, total mole number, and so on. We can continue the chart and so. And X is a symbol for all the other global variables, which can be considered non-equilibrium variables, as we know that in equilibrium, they will disappear. It is a good thing that I need their presence, but at the end, at the final results, it will be a nicer representation for them. here will come the first deviation from the usual energy conservation law. I write that the total energy change consists of the heat, the thermodynamic work. Thermodynamic work is the work which is associated with the transfer of the extensive variables, as for instance, the volume work or chemical work. And dW is for all the other work, so which is not thermodynamically. I use the name for it mechanical work, so but mechanical means non-thermodynamic. And by the help of this definition, I define Joule process. Joule process is when there is no heat and there is no thermodynamic work. So from thermodynamic point of view, it is an isolated process, but non-thermodynamic work, as for instance, electric work or mechanical work, can be taken out from the system. And I call it Joule process because Joule basically planned the arrangement. He used it only in one direction, that mechanical work was injected to the system. But if you have a good imagination, you can imagine this process working in both directions. So that is, and now I define a new quantity, active energy. Active energy is the maximum work which can be obtained from a system in Joule process. So it is when there is no heat and there is no thermodynamic work. On the basis of thermodynamics, from the first and second law, naturally tells us that it is a state variable of the thermodynamic system. If it would not be a state variable, then naturally we could define a wonderful perpetuum mobile. I call this quantity active energy because it is in a very close relation with the vis-viva concept of Leibniz. Naturally, he lived in the 17th, 18th century, at the beginning of the modern science, or before it in some sense. So there is a confusion, and it is hard to really to translate our language this concept, but vis viva in a lot of places when he uses is basically the active energy. And if you translate the vis viva to English, then we know that the vis originally literally means force, but later this force was transformed to energy, so it is energy, and viva is translated as active. And we can count the properties of active energy. So active energy depends only on the non-equilibrium variables. Again, with a simple experiment, simple thinking you can weigh, otherwise, again, a violation of the first or the second law would appear. By definition, it is always positive. It is zero in equilibrium. And the second law says that active energy is dissipated. And the dissipation is always positive. So in a Joule process, the change of active energy is the mechanical work minus the dissipation. We know the energy really this second law that the active energy is dissipated historically is the first formulation of the second law. There is a forgotten paper of Kelvin that he published in 1852, and the title is A Universal Tendency in Nature to the Dissipation of Mechanical Energy. So it is really this second law that what we formulated, that the active energy is dissipated. I did not use the name mechanical energy, but I selected the active energy partially to remember Leibniz. Second, the mechanical energy has a different connotation these times. I looked for the literature, and what I found with this paper, that some historians try to understand Kelvin's paper in modern thermodynamics, so in this equilibrium-based thermodynamics, and they didn't succeed. Okay, so we could see that active energy is dissipated, so its quantity is decreasing, so it demands for another energy which is increasing. And I define the difference. So the difference of the total energy and active energy as a holistic internal energy. One cause for the name is that in equilibrium, it will be equal to the equilibrium internal energy. And we will see that it has the same role, and the holistic entropy will depend on the holistic internal energy. And so, but it is absolutely different from the equilibrium internal energy, because in the internal, what we introduced in equilibrium thermodynamics, that the internal energy is conserved. So it is conserved if there is no dissipation of active energy. And I have to mention that in the present literature, there is a third internal energy, because statistical physics uses our energy as internal energy. But I think so there will be no confusion. U is the internal energy in equilibrium approach. U star is the holistic internal energy, and E is for the total energy. U star, so the holistic internal energy, is the energy also of the equilibrium state, which is reached when all the active energy disappears from the system. So we made a reversible work. And in this stage, we can define a holistic temperature. So it is the same relation as in equilibrium state, and the holistic pressure. It was only an abstract notion. I will show that really they are the temperature and pressure. But now I can describe the balance equation for these terms. here is the energy conservation law, which shows that energy consists of energy change from heat, work, and thermodynamic work. And what I know from kitchen experiences, that if I give heat to a system, then one part will go to heating, and the other part will increase the active energy. When the cover starts to move or the water itself begins to move, then I can say that the heat transfer causes active energy. And so and that is with the work. I don't know this division, so I introduce L star and dq star. This is the part which goes to holistic internal energy, and the remaining part goes to active energy, and naturally the mechanical work goes directly to active energy, and there is a dissipation. To be shorter, I will discuss only the volume work. You can imagine all the other works listed, and simply a longer sum would be to this place. And in case of volume work, I know what is it. Sorry, I missed the minus sign. So there is a minus sign, and then that is the volume work. It is not. If I put it back to this, then I introduce the effective heat, which is the dq star, so that directly for the heating effect, the heat, plus the dissipation. And it equals to the holistic internal energy change plus pressure plus dV. And this equation shows a very important thing, that the effective heat is determined solely by the change of the holistic parameters. So this effective heat does not depend on X or D separately, but it is the same for all processes where the U star weight is the same. So this effective heat is the same as when we do the process without any dissipation, so in a reversible process. And in reversible process, the nice formulation of the Cardinal result. So the Cardinal result that for a reversible cycle, this integral is zero always. So here is a difference with the equilibrium foundation, that the heat was different, and so here was an inequality. But now this inequality is changed to equality. And the result is, if we go back, that this Pfaffian has an integrating multiplier. So it is a derivative of the function, and I call it entropy. And it is defined naturally as the effective heat, but divided by the temperature. So, and this entropy exists for all non-equilibrium systems. That is the first important property. The second important property, that this entropy depends only on the holistic parameters, So somehow it is a measure of equilibrium as the non-equilibrium, the active energy does not appear in entropy. So that is the basic result. So for every system, and now I can really write the balance equation where already known terms appear. And from this equation, we can say that this holistic temperature and pressure are really physical properties as the temperature and pressure because they govern the processes. If I have a non-equilibrium system, that the condition for the heat transfer is that the source temperature must be higher than the minimum temperature in the non-equilibrium system. But what I get, if the source temperature is smaller than the holistic temperature, then active energy will decrease by the heat, and the active energy will be carried to the system only when the source temperature is larger than the when the holistic temperature, and similarly the volume work carries active work when the holistic pressure is higher. Sorry, when the external pressure is higher. Now I go to irreversible or modern thermodynamics. So the difference of modern thermodynamics and the holistic thermodynamics is the appearance of A. The active energy is not present in modern thermodynamics, and it is clear that if I investigate steady state processes, in that case, the active energy will not change, and the increase of active energy is dissipated. And so if I use these relations, I get the balance equation for the internal energy in this form. So it is almost good, but here the external temperature and the external pressure appears as it is well known. And we get irreversible thermodynamics if we go further, and we look for a continuum case. And with a simple transformation, we see that in reversible case, so in these cases, we can assume that the temperature difference is negligible, and so we get back the usual, the normal equilibrium thermodynamic relation for the internal energy. And we can see that this approximation is very good for slow processes. And so really irreversible thermodynamics is a very useful and effective approach for slow processes. For quick processes, it is not because then we have to take into account the active energy too. but the basic problem that we could see that entropy does not depend on the active energy, and active energy is not a good quantity for biology because it depends on the non-equilibrium variables and it is impossible to calculate it. So the next step is to find a form when something useful for biology can be calculated. And here comes thermodynamic, basic thermodynamic property, what we can see from the definition of entropy in this, with this equation, that there is a freedom. We can use ecoentropies where K, A, B, C are constants. These all satisfy this circular integral zero condition. So we are free to select this constant. But we can look for this constant if we ask what is the meaning. And we can see that these constants will modify the place of the position where the ecoentropy maximum appears. So we are free to select the physical state where our ecoentropy will have a maximum. It does not changes the absolute zero because then one party is infinite, so a constant doesn't matter. But it changes the place of maximum. So it means that we are free to select the physical state to which the maximum belongs. Nevertheless, the additivity criteria requires that we have to select the same constant for all systems. Otherwise, we cannot sum up the ecoentropies. And for physicists, there is a special state because physicists deal with the whole universe. And so there is only one natural position for this maximum. As the entropy is an increasing function of internal energy, the only choice is the unavailable infinite energy state. And in this case, we have to select A0 and T1, and we get back the Kelvin scale. So we will get back the same nice property that entropy does not change in quasi-static adiabatic processes. So this original Clausiusian definition is replaced by this postulate.
I just want to interject. There's five minutes more, please. No, we have to stop at 5 minutes. So,
Thank you. And for biology, we have another specific reference system that is the anthroposphere. So what I propose, we select the temperature, average temperature of the anthroposphere, and similarly the pressure, and T equals -1, and I will get a quantity what I call extropy, and it has the nice property that it is zero when the temperature agrees with this, with the atmospheric temperature, and the pressure also, and it contains the active energy, and so it has the property that it is always positive, and somehow it measures the information content of the message that it is a system and it is not an equilibrium state in the anthroposphere. So that is the basic advantage. And the more important, that is the most important property, I can rewrite it as a sum of positive terms. And the first positive term is somehow connected with the energy, the temperature difference, the second with the pressure difference, and so on. And here comes back really the form, which is very important, and we can define it. And the most important why it can be calculated, also we can do the continuum approach. And in this approach, the non-equilibrium will be split two parts. One is a thermodynamic non-equilibrium, which is in the first term, and it can be easily calculated. And in the expression only, the local non-equilibrium remains. Again, it is already feasible.
I could remind you to wrap up, please, just 2 more minutes.
Okay, so that's it. We can calculate, because for equilibrium system, it is the same. Oh, then this part that it is really answers for the question of Schrödinger, why do we eat? We eat extropy. And I wanted to show you that the importance of thermodynamics is very important. It is one of my favorite paintings. Agustin Huller did it. The title is "Wake Up, Black Entropy is Coming." And in summary, what I wanted, I want to summarize. I hope I showed you that this non-equilibrium foundation is a feasible way, and it is much simpler than the traditional one. And the cause of this simplicity is in the fact that Clausius solved the unsolvable problem. Second law deals with the non-equilibrium system with processes which are not present in equilibrium. And that's why equilibrium thermodynamics is so difficult, and that's why this non-equilibrium foundation gives a simple, straightforward thermodynamics. Thank you very much.
Thank you very much, Professor Martinas, for that very thorough exposition. Left me wanting to go back and review thermodynamics from the beginning. If we have one quick question, I think we can take it. Otherwise, we'll have to move on to the next speaker.
Have you actually used the equation with real data?
Sorry, I did not hear the question.
Have you actually used your general equation for real data? Have you actually used numbers?
Yes, yes.
For the equation?
Yes, I did it. Basically, this method was applied, and extropy basically was formulated first, and for an economic problem, that how to characterize the industrial processes by this, by thermodynamics, by entropy, and we worked out a method, and we calculated it. But as a simple answer for your question is the following: what you could say, that in some simple cases, it can be